Double integral has many applications. One of them is the mean or average value. Let me start with a simple example. If we have two real or complex numbers, a1 and a2, we can sum them and divide by 2, and we call it the mean. If we have more than two values, we can call them a sub I, that means a1, a2, a3, a4, and so on, and we sum for I running from 1 to capital N when we have n numbers, and we divide by n, and we can call it the mean. Or if you like, you can write it as sum of ai divided by sum of 1, I running from n, from 1 to n. If we have a function, say continuous, not necessarily continuous, integrable over some interval, then we can take the integral and divide by the length of the interval, assuming a is less than b, and we can call it f average. If you like, you can write it as integral of a to b fx dx divided by integral of 1 dx. So that was for a function of one variable, and for a function of two variables, we can consider the function fxy, integrate dx dy over some domain D, and we divide by integral of 1 dx dy over D. Well, and this can be called the average or the mean value of the function f in this domain. Now that it depends not just on the function f, it depends also on the set D. This is important. The same function, when averaged over a different set, may give a different value. Well, and this expression alone is also interesting. This is the area of the set D, sometimes called measure, and denoted by mu of D. An example, a measure of a rectangle with sides delta x and delta y is just the area, delta x times delta y. Measure of a point is 0. Measure of a line is 0. Well, and similarly, as for a function of one variable, there is a theorem that when the function is continuous, then there exists a value c in the interval ab such that f and c is equal to the average value. This can be visualized by the following picture. If we have a function like that, then there is some number c where the function value is equal to the average value. In other words, the area of the region bounded by the graph of the function is equal to the area of the rectangle. This area is equal to the area of the rectangle with the same base of length b minus a and the height equal to the average value. Well, and similarly for a function of two or more variables, if the function is continuous, then there exists at least one argument, this time a pair xy, such that the function value at this interesting xy point is equal to the average value. Note that this is not true for isolated points. There is no index I such that AI, or they, is not necessarily an index I such that A sub I is equal to A average. If you take 5 and 7, the average is 6. And none of these values is equal to the average value. So the condition that f must be continuous is important, because if f looks like that, then the average value will be somewhere here, and for no argument, this average value is attained. F must be continuous for this C to exist.